Okay. So like I was saying, um, the starter module 2 is going to actually be working on some applications of integrals. I'm sure that as you've been working through the review for test 1, it kind of feels like, okay, we're just doing some integrals, but we don't really have any real world applications and when this is going to be useful. Module 2 is really where you start to see some of the uses of these integration techniques. So section 7.1 is titled The Area of a Region Between Two Curves. And so we're going to be using integration to sort of find these weird areas between two functions. And it's really a simple set of concepts here. So given a function f and g that are both continuous over some interval from a to b, you can find the area of the region between their graphs via subtraction. So if you think about this diagram that I've drawn here, we're trying to find the area between this function f and this function g that lies between or on the interval a to b, right? So we just want this shaded region between these two graphs. There might be a little bit more area between them, but right now we're just focused on the area from a to b on this interval, right? Well, if we want to get this area, we can think about like the integral as finding the area under a single curve and bounded between that curve and the x-axis. So, for instance, the area under the function f over this interval is just the area below that graph f. Similarly, the area below or bounded between the x-axis and the function g is just this area here that I've shaded in red. Okay. And if we just think about like visually subtracting, taking this larger area and subtracting this smaller area underneath it, then we could get this image here, right? Where we're just getting this chunk, this region between those two functions. Okay. So if f and g are continuous on this interval from a to b, then and the function g is less than or equal to the function f for all of its x values on that interval, then we can simply find that area between the curves by subtracting the two functions and then integrating from a to b. Okay. So I think the notation looks really intimidating when you first get exposed to it, but this really is just like, if you had a shape like a square and you're trying to cut out a circle, well, you could find the area of these things separately, or you could just make some sort of new composite function by taking the function that's above, right? So f is this curve that is greater than this curve g, and then subtracting them to sort of get the subtraction of those two functions, and then integrating that new function that you get. Okay. So that's the gist here. Okay, so let's look to our first example then. And this kind of, I would say like this part of this course kind of requires you to be able to visualize these graphs and also draw semi-decent sketches of what these graphs look like. So for instance, if we're asked to find the area of the region bounded by this function y equals x squared plus 2, can you guys tell me what kind of function this is or what that graph will look like, even without throwing it into a graphing calculator? Any ideas?
Parabola.
It's a parabola, right? So like I know that if we have x squared, that should look something like a parabola, either upside down or right side up, right? So if I have that function here, x squared plus 2, then that's just going to be a right side up parabola that's kind of been shifted up on the x-axis by 2 units. Okay. And this other function that they gave us, y equals negative x, is a linear function that has a negative slope. So that function, negative x, is simply just a graph that looks like this, right? So if we were to put those together just to draw a little diagram, we want to sort of draw our y-axis here, draw our x-axis there, and then we only care about the interval from 0 to 1, right? So we really want to sketch this thing out, starting at 0 on our x-axis and going over to 1. And I'm kind of exaggerating this so that we can see it a little bit better. Obviously, if I were making a tiny little graph, 1 wouldn't be a huge step out here. But since that's the only interval we're concerned about, we kind of want to zoom in. Okay. So let's focus on our first function. Maybe you could call this one f, right? F of x is equal to x squared plus 2. What we want to do is find its endpoints on this interval. So like I'm just going to plug in f of 0, which is going to be 2, right? Because I'm just plugging 0 into the function to find that endpoint. And then also f of 1, and that's going to be 1 squared plus 2, which should just come out to 3. These are going to be the endpoints. Right, so now I can plot them since I have 0, comma 2. This will be 0, comma 2 up here. I'm just going to label that 2. And then 1, comma 3 is going to be higher, so maybe I should have done a little bit more justice to this y-axis here, or place that 2 a little bit lower, but that's going to be 1, comma 3. And then I know that this is a parabola, right? So that curve should look something like, like that, roughly speaking. Okay. We can do the same thing for the function y equals negative x. You could call it g of x instead, equals negative x, but we still need to find those endpoints if we want to graph this. So g of 0 is going to be equal to negative 0, which is just 0. And then g of 1 is just going to be equal to negative 1. So those are our endpoints there. And obviously, you know, if you work with pencil, this will make a whole lot more sense because I won't have to like scratch anything out. Or like if you see my y-axis here, negative 1 is going to be below the 0 on the y-axis there. So we'll have 0, 0, which is this point here. And then we have g is 1, negative 1, so that's going to be over 1, down 1. So something like this. And if you have a straight edge, that's great. If you don't, you're just going to let go and let God. But luckily, I brought this little straight edge here to make my graph a little bit prettier. So what we're actually doing is trying to figure out this area between these two functions, right? It's kind of like a horn shape. And that's just me trying to give a label to what we're looking at because like you should understand the shape of this thing so that we can find its area. Obviously, this is a non-standard geometric shape, right? Like it's not a triangle, which we have a formula for. It's not a circle. It's not a rectangle. It's something smoother and curvier on one side. So sort of like a weird trapezoid looking thing. Okay. But how do we find this area? Well, if we go back to this idea that the area of this new shape is just going to be the integral on the interval, which is going from 0 to 1, then all we need to do is take the function that is higher up, or the larger function, which is f of x. So I'm just going to write that as f of x minus the function that's lower. And since I coded that in red earlier, I'll go ahead and keep that color coding here. So g of x, I have to subtract those. And then whatever I get from that, I'll go ahead and integrate. Okay. So we could do it all inside the integral right now, but I think that gets kind of messy. I like to always do my scratch work over here to the side, as I've already started with my graph up here. So my scratch work is simply going to be, let's take our function f of x, which is x squared plus 2, and we're going to subtract the function g of x, which is this negative x here. Okay, so just be very careful here because when we're subtracting, we want to always put that in parentheses because if we have more terms in this function, or if we have a negative sign, then we're going to be subtracting a negative. Okay, so be very careful with that because the signs are going to matter. This thing is going to be what? X squared. Now it's going to be a plus x, and then a plus 2. I'm just rearranging the order. And this thing is what we're calling f of x minus g of x, right? So I can go back to my integral and say, okay, we're really just taking the integral from 0 to 1 of this thing that I found, which is x squared plus x plus 2 dx. Okay, so that's not too terrible of an integral because we're not having to use any of our, inverse of trigonometric functions. We're not using our ln rules. This is just strictly the power rule. So if we integrate this, we should be getting what? 1/3 x to the third power plus 1/2 x squared plus 2x. Okay, just applying that power rule. And then we're just going to evaluate this from 0 to 1 to find that definite integral. And so we'll start off with 1, which is going to give us 1/3 times 1 to the third power plus 1/2 times 1 to the second power plus 2 times 1, all of that, minus 1/3 times 0 to the third plus 1/2 times 0 squared plus 2 times 0. And the nice thing is that these all amount to 0, right? So we're not really subtracting anything there. Let's see if I can move that up. There we go. And then you get your trusty calculator and let the calculator do the arithmetic for you because, I mean, I think a lot of the thinking here is just done before we get to this calculation part. So let's go ahead and do 1/3 times 1 is still going to be 1/3 plus 1/2 plus 2, right? And I'm getting 17 over 6, okay? So I'm just going to write over here, at the risk of squeezing this in, 17 over 6. Presumably that's square units because we're talking about area, but that's going to be the area, right? So any questions, comments, concerns about that example? Does that feel okay? Let's do another example, right? Because having a couple of examples is going to help us out more than just the one. On the next set of notes, for the second example, we want to find the region or the area of the region between two intersecting graphs. Okay. So we're going to find the area of the region bounded by these two functions. F of x is equal to 2 minus x squared. Again, noticing that that's an x squared, we know that that's going to be an inverted parabola. And then g of x is going to be equal to just x, right? This sometimes is called the identity function. It's just a straight line with a positive slope. But we want to get that drawing down. So I'm going to be very careful about how I draw this. And I'm going to use the pencil now, okay? And draw the full x-axis and y-axis here in case we need more of the graph, okay? So we'll start off with the endpoints here, or actually the points of intersection, because like as the notes here indicate, these graphs are going to intersect at more than one location. Okay, so in the previous example, we weren't concerned with the region or the interval where these two graphs were intersecting, right? Presumably, if we trace this graph down here, g of x, backwards on the x direction, eventually it would maybe intersect that parabola, but we didn't actually get to see that and because we weren't concerned about that interval. But now it doesn't even specify what interval we want, right? So we have to find where do these two functions intersect. And so to find their intersection, all we need to do is set these graphs equal to each other, okay? And what I mean by that is literally we're going to take 2 minus x squared We're going to set that equal to x, and then we're going to solve this equation. Okay. And you'll notice here that as we start solving this equation, it's going to be a sort of a flashback to some algebra stuff. I'm going to go ahead and say I tend to prefer making my x squared positive. So I'm going to add the x squared over to the other side. And I'm also going to subtract this 2 over to the other side. So the equation now becomes 0 equals x squared plus x minus 2. Okay, just some basic algebra. And the reason why we want to set this equal to 0 is because now we want to factor this because this is a quadratic equation. Okay, so is this factorable if you guys look at this polynomial here, x squared plus x minus 2? Anybody not sure? Uh, are we able to factor this expression here, x squared plus x minus 2? Can we factor this? Or are we kind of rusty on factoring? A little bit rusty on factoring. Okay. Okay. It seems that Jasmine in the chat has it factored. I'm going to go back in time to say let's grab a scratch sheet of paper and just kind of remind ourselves of some of our factoring techniques. So like if I have x squared, what was it? X squared plus x. Sorry, not plus x, not plus 2. X squared plus x, and then what was it? Minus 2. There was this factoring method. I'm not sure if you guys learned it when you guys were in algebra, but where we would take this A, B, and C, and if you multiplied A times C, -2, we would then look at what are all the factor pairs of -2. So that's like 1 times 2. And we want to find the pair of factors that are going to multiply to give us the -2. Okay, that's going to be our A times C. But they also need to add to give us B, which is just 1 here since that's the coefficient. So if I need to multiply 2 of these to get a -2, well, obviously I only have one option here, which is 1 and 2. One of these needs to be negative, though. So we had to choose which value is going to be negative. And both of these conditions need to be met. So I know that the 2 needs to be positive and the 1 needs to be, yeah, there we go. The 1 needs to be negative. Okay, so it needs to be -1 and +2. You guys might have seen this written like with an X symbol where you write A times C here, which is -2, and then the B is 1 down here. And then you're looking for the factors of -2 that will add to make 1, which is this here, -1 and +2. So that's how we know that this is going to be x minus 1 times x plus 2. Okay. Okay. And if some factoring stuff comes up later, then we'll kind of have to approach that and like do something more complicated. Another way of thinking about this was that this was a pretty simple one where we could have just said, okay, well, what are the factors of -2 that will add to give us 1? Well, that has to be these guys. Okay. So like I said, if we see some other factoring, hopefully a little bit more complicated so that we can get just another refresher in factoring, then we'll do that. But we're going back to the original problem. This factors into, we said, x minus 1 times x plus 2 equals 0. And then when you're solving quadratic equations that you've put in factored form, this just amounts to saying, okay, well, now I can use something called the zero product property. X minus 1 equals 0. X plus 2 equals 0. If we solve these, we can find those x values where our two graphs intersect. So this is just going to be x equals 1 and x equals -2. Okay, so that's where the intersections are happening, which means now on my graph, I need to go out to -2 on my x-axis, and I need to go out to 1 on my x-axis also. I'm going to make this a little bit bigger just so that maybe my picture looks clearer. So I'm going to make this one -1 and make this one -2. And I'm going to make this one a +1. Okay. probably drawing the pictures of the graph is the most like cumbersome or the most like labor intensive part of this process. But now we have to find those endpoints. Like where do those graphs actually intersect each other? So if we take x equals 1, sorry, let's go from left to right. Let's start with -2, right? So if we start with x equals -2, then we can find f of -2, which is going to be 2 minus -2 squared, which is 2 minus, that's going to be +4, which is going to be -2. So I have the ordered pair -2 comma -2. I hope I didn't back myself into a corner here, at least when I'm drawing these graphs later, because I'm going to have to go down -2. Um, then let's go with g of -2 so we can get the endpoint over here, which, if we notice, um, should be the same thing, right? Because we're just plugging in -2 there. So we're getting -2, -2 when we plug that x value into this function. Okay. So these are going to intersect on the left side at -2 and then down 2. I'm just going to call that right here, call that -2. So that's going to be right here. That's one intersection point. Okay. And then over here, at this intersection point, hopefully it's going to be a little bit higher. We'll go with f of 1, which is going to be 2 minus 1 squared, which is just 2 minus 1, which is 1. We could have used our calculator for these to make it easier, but it's always good to sort of practice some of the fundamentals. Then we're going back with g of 1 to find the endpoint for this graph, but you guys probably have picked up that that's going to be 1, 1, which is the exact same point. So really, you just need to find the intersection once. You don't have to do this extra work here, but it's good to be able to make that comparison to say like, oh yeah, based on that quadratic equation that we solved, if these are the intersections, then we should be landing on the same point for these endpoints. Okay, so this one's going to be at 1, comma 1, which is going to be up here. Let's call that 1. And now let's draw those graphs. So we said f of x was this inverted parabola. So maybe, if you really wanted to, you could graph this in your graphing calculator to see what the shape actually looks like. I'm just going to go ahead and eyeball it somewhat and say if it's an inverted parabola, it's got to look something like this, right? Kind of that inverted parabola shape. And then g of x, that is just a linear function, so it should just be a straight line that connects these things. Realistically, it should cut through the origin since that's just going to be a 0, 0. But my drawing isn't very good. Even if I try to salvage it with a straight edge, it's not going to be perfect. So just know it's not going to be a perfect representation of what these graphs actually look like. But if you were to graph this in your calculator or on Desmos, you would see this kind of like, I don't know, fortune cookie type shape, this kind of crescent, right? So we're looking for this area between the two curves, between its two endpoints. Okay. So just know now that we have those endpoints, we have these x values where those graphs intersect. That means that the interval that we want is going from -2 to 1. Okay. And let's just take a breather there. Do you guys have any questions? Does that feel like it's a doable process to graph these things? Any input there whatsoever? We need more examples, right? Um, and like I said, I think that Desmos.com, the graphing calculator, is always going to be a really valuable tool because, like, let me just share that for a second. Like, this was a lot of work doing it by hand. And God knows that we're no longer in the 90s or in the period where we're doing everything by hand. So, like, we could have simply typed in f of x is equal to 2 minus x squared in Desmos, we got that function. Then here we'll put g of x for our other function equals x, and we get these two graphs. And then if you want to limit their, how far these graphs go apart, you can use these braces and say, okay, well, we want to go from -2 to, and I'm going to put x in the middle. We want to go from -2 to 1. And it doesn't matter whether these are less than or equal to or less than, because Desmos isn't that like picky. But we're going to use that same interval here. We're going to go from -2 all the way to +1. Right? And so that's the shape that we're looking at. And those intersection points are where we said they are, -2, 2, and 1, 1. And we're trying to find this weird crescent shape. So like my drawing, my representation isn't as like arched as this quadratic that they have here. But a picture is not the same thing as the function. It's just like a guide, right? So ours doesn't have to be perfect, but the math is going to work out. Okay, so we're looking for this area that's in between these two curves. Okay. So when you're working on the homework, if you're not sure how to visualize the function, there's a lot of like little technical details we could go into for the algebra to like get better resolution of what this function is supposed to look like. But what I would say is if all else fails, at least when you're working on the homework, and you're practicing, you're drawing these graphs, it's not making any sense to you, then just open up a tab and go to Desmos and type those functions in just so you have like a clearer picture of what those graphs should look like. Okay. So let's go ahead and go back to the problem we're working. Okay. So again, this isn't an art class, so our picture doesn't have to be a perfect representation. We just needed to get that image because like I'm sure that when you guys, have been working on the review for test one and you've been doing those integrals, like if you can't visualize something, it's hard for your brain to grasp that concept. So like we really want to practice drawing these pictures so that we can grasp what's going on because when we get to section 7.2 and 7.3, the pictures are going to be very important. So if you don't consider yourself an artist, then you're going to have to practice to become slightly better of an artist than you are now. Okay. But getting back to it, we want to get this area, right? And we know that the area is going to be equal to the integral. Now we know that that's going from -2 to 1. And then we want to subtract the function. So we're going to do f of x minus g of x dx. And just be very careful here. Like if we wanted to find the region between these functions, we need to make sure that f of x, whatever we put here in the front, is truly the function that's on top of our picture, right? It's this blue function up here. That parabola is above, it's greater than or equal to the function that's below it. So g of x, whatever we call g of x, that needs to be the function below or function on the bottom. Okay. Otherwise, you might get close to the same answer, but the sign might be wrong. Okay. So just make sure when we're doing subtraction, or just like we're doing subtraction in grade school, if you have like 5 minus 3, you're going to get a +2. But if you have 3 minus 5, if you flip it around, you're going to get a -2, right? And we want to make sure that we're getting the right signs there. So we're going to do that scratch work. So now we're going to actually just find that subtraction, which is 2 minus x squared. Okay, that's our first function, the one that's on top, minus, and I'm just doing the parentheses just to practice safe math here, because if this was a more complicated function, then maybe we'd have to switch some signs. But luckily, we didn't really have to switch any signs there. I'm going to rewrite this and say, let's put it in order. -x squared minus x plus 2. That is f of x minus g of x. Okay. And I'll go to another sheet of paper just to finish this up since I don't want to squeeze it in. Okay, so the area that we're looking for is bounded from -2 to +1. And this function subtraction that we did should be negative x squared minus x plus 2. Negative x squared minus x plus 2. Okay. So that dx. And then again, the integration is the easiest part of these problems, right? So like the calculus is actually straightforward. It's the algebra, the graphing, finding the endpoints that is the most complicated part of these problems. So if we integrate this, then we should be getting what? Negative 1/3 x to the third power. We should be getting negative 1/2 x squared. And then we should be getting positive 2x. And we're evaluating that from negative 2 to 1. So that's going to be negative 1/3 times 1 to the third minus 1/2 times 1 to the second plus 2 times 1 minus, then we're going to do negative 1/3 times negative 2 to the third minus 1/2 times negative 2 to the second plus 2 times negative 2. And notice as I was writing all of those down, it's a lot. It's a lot for me to keep track of. There's a lot of little details, a lot of places to make mistakes. That's literally why I was dragging my finger across this function each time I plugged in either the 1 or the negative 2 so that I could keep myself mentally on track. Okay? Because I don't want to make those little mistakes because you might be doing all the calculus perfectly, but if you lose a negative sign or if you plug the wrong number in for one of these coefficients, it's all over. Okay? So if we go back here, we could throw this whole long expression into the calculator, but I'm just going to simplify some stuff by hand. So this is going to be a negative 1/3 since that guy is just going to be 1. This is going to be a negative 1/2 since that guy's just 1 plus 2. Then be very careful. Let's go ahead and simplify this on the inside first. That's going to be a negative 8 since negative 2 to the third power is going to be negative 8 times a negative 1/3. So that's going to be a positive 8/3 inside here. This guy is going to be, let's see, it's going to be a positive 4 times a negative 1/2. So that's going to be a negative 2. And then this is going to be a negative 4 out here. But we can't forget that they're all going to be switching signs since we have this negative on the outside. So this is really still has this negative sign from here. So if we write it all out, negative 1/3 minus 1/2 plus 2, that one's just fine. But then we have a minus 8/3. We have a plus 2. We have a minus 4. And for the love of God, I hope that this sign turns out to be correct. So at that point, I'm going to say I'm exhausted. Let's go ahead and throw that in the calculator. Negative 1/3 minus 1/2 plus 2 minus 8/3 plus 2 minus 4. And I'm getting a negative 7/2. Negative 7/2. So where did I go wrong? Right? Because if we look at our diagram, this should be a positive area, right? Where did I possibly go wrong? So when I subtracted these, I took the top function minus the bottom function, negative x squared minus beta a. That one should be good. I wonder if maybe if I had evaluated it and not doing a bunch of stuff by hand, if it would have been better. Just checking. Let's see. Okay. Mark is asking in the chat here, how do we know it should be positive? Well, there's two reasons why it should be positive. First, whenever we're talking about area in mathematics, areas are always given in terms of a positive area. Okay, by definition, areas are always positive. If you think about this in terms of physics, there's no such thing as a negative area, right? Like um, an area is bounded by two lines. So if we think about this as like drawing the area of a rectangle, if you go out in one direction and then out in another direction, then this distance has to be positive, right? Has to be a positive distance. And then also this distance up here has to be positive as well. So if we're multiplying positives to get the area of like this rectangle, then the area has to be positive since we're multiplying two positives. But getting back to this function that we just drew, if we did this correctly, this higher function up here was the one that we put first in our subtraction. And so like the values of the function g are below the values of the function f. So if you take like a bigger number minus a smaller number, then that subtraction should result in something positive. So that's why, like, having done this problem and then getting to a negative value, that's telling me, like, oh, I made a mistake somewhere. Like, the number might be correct. And in fact, when I check, um, the number should be correct. I'm just going to double check this. We got negative 1/3, negative 1/2 plus 2x. So possibly we just evaluated this wrong. So I'm thinking that maybe when I was doing some of this arithmetic in here, that I just made some mistakes. Okay. Negative times a negative would be positive. Negative, no, that would be a positive times a negative would be negative. That would be negative. So then if I flip the signs, there it is. Negative times a negative is a positive 4, right? And I had done negative 4, and I left this one as a negative. So if I put this in the calculator now, actually, let me just go back to my entry here. Yeah, see there? I entered a -4 when it should have been positive. So, I mean, that's a really nice thing about these problems. If we know the area is supposed to be positive, if we get a negative result here, we know that we've done something wrong. Okay. And I know that you guys have probably had this experience where, like, if a teacher messes up an example in class, like, it really throws you off. But, like, in calculus, this is a really like teachable moment, right? Because like when you're working on these problems, what if you get a negative, right? That tells you that you did something wrong with your arithmetic. And the thing I love about math is that it's humbling, right? If you know this should be positive and yet you get a negative, that tells me that I did something wrong. So again, fixing that value, I got 9/2, which is a positive value. So this was bad arithmetic on my part. And I know that the actual value should be 9/2, which is the correct area. I just forgot to distribute that negative correctly. And again, I said this when we started, like there's so many little places where you can miss a negative sign, and that's exactly what I did, right? I kind of cursed myself going into that problem. Okay. So, if this feels overwhelming, it's just going to take some practice. And it takes a keen attention to detail, right? And there's nothing more I can say about that. These are just going to be trial and error, but you're not going to get better at it, or if you rush the process, or if you procrastinate and put your homework off until the last minute. So like that's why I keep on recommending that if you guys are struggling with any questions at all, any of the problems in the homework, pop into Math World. You don't have to come to campus, right? You can go through Zoom, ask them like, hey, I keep getting this one wrong. I think that something's wrong with my arithmetic. I know that this answer should be positive. What's happening? And the tutors will walk you through the problem, and they'll be able to compare and see like, okay, well, where did the mistake happen? Because at this point in Calculus 2 and in upper level math, like you have to regulate yourself and you have to check, is this kind of the answer that I'm looking for? Or, is this off because I know that sign is wrong? Does that make sense? Okay. Let's do another example. Okay. Let's hope to God that I don't make a mistake this time. We did two, and now I'm skipping to example four. Okay. Curves that intersect at more than 2 points. So let's find the area of the region between these two functions. These two functions, rather than actually graphing these by hand, because this is a polynomial function, it's a cubic function. I know off the top of my head that this function is going to look something like this. That's what cubic functions look like. And then I know that just by looking at this equation, that this function is going to be an inverted parabola because we have that negative x squared. So I know that that's going to be a negative quadratic. Okay, so if we put these together, we're going to be looking for a graph that kind of looks like this, but then if you throw a parabola in there, um, let's see what that graph should look like. It could look something like this, where we're looking for the area between these 2 points and the area between those 2 points. So like there are two regions between the graphs. And so we would have to look for 1, 2, 3 intersection points. Okay. So like if we were doing this purely algebraically, then to find those intersection points, we would need to set those two functions equal to each other and solve them. Okay. Set the functions equal to each other and then solve the polynomial equation. So it's not just going to be a quadratic equation. Okay. So let's do that purely algebraically, and then we're going to bring in Desmos to make sure that our drawing is looking correct and that the intersections are at the right places. So we'll start with 3x to the third power minus x squared minus 10. That's going to be the function that we called f. And we're setting that equal to the function that we're calling g, which is negative x squared plus 2x. Again, that's the function that we're calling g. Now, similar to that quadratic example that we had before, we just need to get all of these terms on the same side and get the polynomial set equal to 0. So what I'm going to do is I like to keep the term with the highest degree, with the highest exponent, positive, so that 3x to the third power. I'm going to leave that where it is. But I'm going to move these terms, g of x, over to the left side. So I need to add x squared, and I need to subtract 2x. So I'm going to add x squared here, because that's going to be a like term. And then the minus 2x, I'm going to end up kind of just shoving into this equation here, since we didn't have any x terms. Is the minus 10 missing from the x? Oh, is the x missing from that? Yeah, absolutely. Thank you so much, right? The function was negative 10x, not negative 10. So that means that, let's see if I have some white out to make this a little bit prettier. Always do algebra in pencil if possible, right? And I do not have a whiteout rule here, so we're just going to have to do some scribbling. This is going to go here, right? Thank you for catching that, Mark. Really saved our butts here. Okay. So we should be getting then 3x to the third power. Negative x squared and positive x squared cancel each other out. And then negative 10x minus 2x should be negative 12x. Are you guys okay with that? All right. Has anybody caught any other mistakes that I've made? Because I am human if you haven't noticed. Okay. Now, factoring is going to be a very important process for solving any kind of polynomial equation. So just going to write that little note. Factoring is important for solving polynomial equations. That includes quadratics, but even these higher order polynomials. Okay, so if we need to practice some of our factoring, then that's what we need to do. The simplest kind of factoring that you're ever going to do is probably just factoring out the GCF, right? Factoring out the greatest common factor. So if I look at these two terms here, what factor do they have in common? They have a 3 in common. So I'm going to put the 3 on the outside, but they also have an x in common, right? So 3x is what we were looking for there. And if we factor out the 3x, we should have an x squared here. And then this becomes negative 4, correct? Equals 0. So that was just one we factored out the GCF, greatest common factor. Does anybody remember how to factor x squared minus 4? It's a special factoring formula. It's okay if you don't remember it, but you should memorize it. It is a difference of squares. So Jasmine, right on. That's a difference of squares. So I'll just write that down. And we'll say that we'll have the 3x on the outside, and this guy here should factor into x plus 2 and x minus 2. Okay. So the difference of squares formula was just if you ever have a polynomial or a quadratic of the form a squared minus b squared, that can factor into a plus b times a minus b. So that's all I did there. I used that formula. Okay. Nice to have these little snapshots in here. Okay. Now that that is fully factored, I can go ahead and use the zero product property and say, okay, well, if I have 3x equal to 0, that means that x is equal to 0. Okay. If I have x plus 2 equal to 0 and I solve that equation, then that means x is equal to negative 2. And then if I have this one, x minus 2, and I set that equal to 0, then x is going to be equal to 2. So these are the x values where my intersections are occurring. All right. But we want to make sure that even though we solved it in this particular order, when we graph it, it should appear on the x-axis from left to right. So the numbers should be from smallest to largest. So like when we see it on the graph, we're going to see an intersection at negative 2, then at 0, then at 2 in that order. Okay. Like I said, I wanted to maybe spare you guys the grim reality of graphing this by hand, and let's just go ahead and pop over to Desmos to get a sketch of this graph, right? If you wanted to, you could plot both of these functions on your calculator here, right? Just by going here and typing 3x to the third minus x squared minus 10x. There's our first function. And then for the second function, we'll do negative x squared plus 2x. Do you remember how to graph that in your calculator? We just go to the y equals to do that. Once you have your graphs typed in, we can go ahead and graph that. And then notice that, if we wanted to change these intervals, we know that we only really want to see the graph from negative 2 to positive 2. So you can change the window setting here. And I'm going to go maybe not to negative 10. Let's go a little bit closer in. So let's try negative 5 to 5. And I'll leave the y-axis alone. So I'm not going to change the y values there. Go back to the graph. Let it sort of render here. And so we're looking for these two regions here for our graph that kind of look like this drawing that I did before. Okay. Again, Desmos is a much nicer graphing calculator. So let's sort of pop over there just shortly to see what this graph should look like. Right there. Let's delete these graphs that we had before. And now I'm just going to type in the exact same thing. So f of x is equal to 3x to the third power minus x squared minus 10x. And we just wanted that between, so the x values need to be between -2 and +2. Let's see, where's that brace? Then g of x is equal to -x squared plus 2x, and we're going to bound that between -2 and +2, like so. We could always change these colors. I'm going to make blue for the top graph. I'm going to make red for the bottom. I mean, but it's kind of hard because they switch sort of directions. Let's change the window viewing here. So the x-axis, I'm just going to go from -3 to +3 so we can see the graph a little bit better there. I'm going to zoom out, drag that up. Can you guys see those shapes? Okay. And notice that they intersect at -2, -8, 0, 0, and 2, 0, right? And that was a lot easier than maybe trying to visualize that on your calculator, okay? So what are we going to do next? Well, we have something to draw, right? So let's get out a sheet of paper and try to draw this curve as best we can. So I'm just going to draw it real quick. I'm going to leave the graph on Desmos up just so that we can see this. I always start by plotting the endpoints first. So I'm going to say this shape looks something like that. We hit the origin. And then this one is kind of curving like that and then hitting the origin. Then it curves up above like so. And then this one curves on the bottom of the x-axis like that before they intersect each other again. Okay. So remember the blue graph here is f of x. And the red graph here is what we call g of x. Okay, and now I'm going to switch back over to my drawing, and hopefully you guys don't laugh cruelly at my art skills here. Right, we have that intersection at the origin. That should be nice. We said that if you're still looking at Desmos, this should have been -2, -8. This over here is God knows what it is. I'm going to just pop back over to Desmos. It was 2, 0. Okay. All right. Now, there's something that you need to watch out for. So we got to proceed with caution here because we have the graph, right? And we found those intersection points, and they're at the x values that we found, right? This is 0, 0, and 2, right? So we could have plugged them into either one of the functions to find those endpoints and then draw them, but I think like if you either use Desmos or kind of use your graphing calculator to get a rough sketch, then we have an idea of these areas that we're trying to find. I need to find this area here. And for this area on the left, notice that the function f of x is above the function g of x, right? So from the interval -2 to 0, right, on the x-axis from -2 to 0, this is the left side. F of x is above g of x. So what that means is if we needed to find this area, we would have to do the area from -2 to 0, where f of x, which is the upper function, we're going to subtract from that the function g of x when we take that integral. But from the interval 0 to 2, the functions kind of switch roles, right? The function g of x is now the one that's above the function f of x. And so we have to switch the order of our subtraction in order to accurately get this area in this region, right? So g of x is above f of x. So the area for that portion going from the x value 0 to the x value 2 is going to be g of x minus f of x dx. Does that make sense? It's like a very minute detail, but it's going to make all the difference here because we don't want to if we kind of had the subtraction switched and we left f of x as quote unquote the top function, then like we would get a negative area for this. And we don't want to get a negative area because then when we add it to the other area, it's going to cancel out, at least in part or maybe entirely. We want to get an accurate representation of these areas. So you do have to watch out for which graph is on top. Okay. So let's break that up into the pieces and we'll go from there. So let's call this area 1 and area 2. Okay. Area 1 is going to be the integral from -2 to 0, where we take f of x, which was the cubic function, right? Which was what? Let's see. That one was 3x squared minus x squared minus 10x. Okay, and we're going to subtract from that the quadratic, which was -x squared plus 2x, -x squared plus 2x, like so. Dx. And this is just me writing it out in total because like if you don't want to do some extra scratch work to the side, then you can certainly do that algebra inside the integral. So that should be -2 to 0. And then this should have been a cubic, so that's a 3. Okay, so that's going to be 3x to the third. Then we're going to have that -x plus an x squared. So that -x squared and the positive x squared here are going to cancel out. Then we have a -10x minus the 2x, so that was a minus 12x dx. And now we can actually integrate that and find that first area. Okay, so if we take that integral, we should be getting 3/4 x to the 4th power minus, so it would be an x to the 2nd power, but then divided by 2. So this is going to be minus 6x squared, evaluated from -2 to 0. So we're just finding that area. That's going to be 3/4. We're going with 0 first to the 4th power minus 6 times 0 to the 2nd power. Then we're going to subtract 3/4, and then that's going to be a -2 to the 4th power minus 6. And that's going to be a -2 to the 2nd power, like so, equals. And then we're just going to throw this in the calculator because I don't think anybody has the wherewithal to do this by hand at this point. I'm also exhausted. So the good news is that these guys are going to be zero since we just have zeros multiplied by these guys. So like 0 to the fourth power is 0 times that's going to be 0. So all I really need to put in the calculator is this latter part. So negative, and then I'm going to put 3/4 times -2 to the fourth power minus 6 times -2 squared. Close up the parentheses there, and I'm getting 12. Thank God. We got an integer, right? A whole number. So area 1 is 12 units. Okay. But we still need to find area 2. So that's A1. This is A2. And for A2, we have to do g of x minus f of x, since g of x is the higher function, right? It's above f of x in this case. So for that one, switch back over. For area 2, we're going from 0 to +2. And for that one, we needed g of x, which was the negative x squared, the negative x squared plus 2x. And now we're subtracting the other function here, f of x, which was the 3x to the third minus x squared minus 10x dx. Okay, so we're just going to do some algebra to simplify this polynomial a little bit more. If you want, you can distribute that negative sign just so that this is kind of easier to look at. Negative 3x to the third plus x squared plus 10x. And now we're just combining like terms with these guys over here. So we should have, I'm going to put this cubic term in the front, 3x to the third. Then we have a positive x squared and a negative x squared. Those guys are going to cancel. And then it's going to be a positive 2x and a positive 10x. So it's going to be plus 12x dx. And thankfully that simplified nice and easy. We only have those two terms. So it should be easy to integrate this polynomial. We should have negative 3/4 x to the fourth power plus 6x squared. And we're evaluating that from 0 to +2. So again, some basic arithmetic. Negative 3/4 times 2 to the fourth plus 6 times 2 to the second. Then we're going to subtract negative 3/4 0 to the fourth plus 6 0 to the second, right? And the nice thing about this integral, this definite integral, is that these terms on the backside, since they're being multiplied by 0, they cancel out. So we're not really concerned about that. I'm just going to throw this first part into the calculator just to simplify my life a little bit. So we have negative 3/4 times 2 raised to the fourth power plus 6 times 2 raised to the second power. And that's 12. So the area 1 and area 2 turns out we're the same. And that's going to be area 2. So the total area, which is equal to area 1 plus area 2, is equal to, I'll just write it here. 12 plus 12 is what? 24. Okay.
That's area 1.
Yes. Okay. So did anybody have any questions about finding area one or about finding area two? Any comments or concerns? And the comments can just be anything, right? How are you guys feeling about that? That felt like a lot, right? Okay. There's no getting away from it. We may have to go back and brush up on some of our basic algebra skills, whether it's factoring, whether it's graphing. Uh, I mean, you guys probably noticed, or maybe chime in. Was the calculus part, was the integration, was that difficult, right? So like I tell students that are in college algebra and below college, below calculus 2, the hard part about calculus is the algebra, right? Because that's the part where the rubber meets the road. We need to be able to visualize these graphs. We need to be able to do some basic things like factoring, like subtracting polynomials. Um, but like it's going to require a ton of patience, right? This is a marathon, it's not a sprint. You cannot rush through these. You cannot put it off or procrastinate because, well, procrastinating is just a recipe for stressing yourself out and then maybe doing the avoidant behavior of like, okay, well, now I'm too afraid. I'm too far behind to ask for help. And I see that in a lot of students. So, um, just understand, like, I am here to support your understanding, but it's going to take a lot of work and practice on your part to get these problems down. Okay. So at the risk of maybe ending too soon, I did have a little bit more on the notes that I had created for today, but I did want to give you guys the last 15 minutes to sort of pick my brain about the test one review. So I'm going to end the recording now and give you guys an opportunity to sort of ask any questions about the review for test one if you have questions.